This video is about how to graph sine and cosine using all transformations, at least all pertaining to what we'll cover in this course. And so what I'm about to write will involve several note items or noteworthy items, which means you may want to just jot this down and keep notes on a piece of paper on your own. I would highly recommend that. And then, of course, we'll eventually get to some examples which use these notes. But likely you'll want to have this written so you can refer back to it also. Let's start by recalling what we already know and have experienced with a sine or cosine graph. We've already seen and even graphed something of the form y equals a times the sine of x, or y equals a times the cosine of x, where a is just some numeric coefficient in front of the trig function. Now let's get some of the specifics down. Again, some of them we've already seen, but this will make sure they're clear. So the absolute value of a, this coefficient a, is what's called the amplitude. That's right, the amplitude. And it determines how high or low a graph spans, as we'll see with examples here. More specifically, if the absolute value of a is greater than 1, then we get what's called a vertical stretch. If the absolute value of a is between 0 and 1, we get what's called a vertical shrink. So the value of a, and specifically notice we're talking about the absolute value of that, will determine how the graph is stretched or shrinked vertically. If this value a, notice I don't have the absolute value this time, but if that value a is less than 0, meaning it's negative, then it will end up doing what's called a vertical reflection, or also known as flip. That's just what happens when you look at the graph. It looks like it flips vertically. And again, we'll see more examples of that. So far, we're only discussing one particular kind of transformation, and it all pertains to this coefficient a, which could show up in front of being multiplied with the trig function. Now let's add more transformations to these functions. To do so, I'm going to write out the general forms that we will be referring to. Here's what they are. So I could write out y equals a times the sine. Okay, we've seen that already, right? The a we just discussed. But now I'm going to add more. So I'm going to say the sine of, I'm going to use a bracket, and then in the bracket, I'm going to have a capital B, and then parentheses x minus capital C, close parentheses, close brackets, plus D. All right, so obviously it got a little more complicated. We added 3 new letters, the B, the C, and the D. And all 3 of those will do things to the graphs, kind of like A did or will do to the graphs also. Of course, this works for sine or cosine, so though it's the same, I'm going to write out the equivalent formula for cosine. Y equals a times the cosine of bracket b parentheses x minus c close bracket plus d. We've discussed a already. Now let's discuss some of these others. Next up, of course, is b. b is going to reveal what's called the period of the graph. Now, we've discussed period already with all of our trig functions, and you might recall some of them are 2 pi, some of them are pi. Well, b is going to adjust the period and possibly change it from either of those. So here's how we're going to determine it. P, our new period value, is going to be the pure period, which is the one you know already for the various functions, divided by the absolute value of b. That's right, so this is in some sense a formula to determine the period p for the given function. And of course, it might not be 2 pi or pi. It could be changed depending on what b is. The pure period will either be 2 pi or pi, depending on which function is. Of course, hopefully you remember periods of pi go for tangent and cotangent, and 2 pi are for all the others. So that's what we'll be using for the numerators, and then we'll be dividing by the absolute value of b, whatever that is in the given equation. More specifically now, if the absolute value of b which we've already used back here, if that is greater than 1, then we end up with what we'll call a horizontal shrink. If the absolute value of b is less than 1, we end up with, you guessed it, a horizontal stretch. Now notice there are some aspects to this that might help you remember things. First of all, when we talked about A previously, that did a vertical stretch or shrink, and you might recall that if A was greater than 1, it was a stretch, a vertical stretch. Well, now notice, if B is greater than 1, it's a horizontal shrink. So those are the opposite. Similarly, if A was between 0 and 1, we said it was a horizontal shrink, but now if B is less than 1, it's a horizontal stretch. So just a question to think about here for a moment. Think about what if the value for B is negative. Okay, just give that some thought. Now, notice that in these two statements, I've made it the absolute value of B, which forces it to be positive. Okay, fine. But what if the value B itself was negative? Look back at the form of these general equations where B occurs. Spend a few minutes, perhaps, thinking about what that would do or mean, and we'll hopefully see that in an example going forward. Notice two more letters in these general forms up here that I have not mentioned yet, C and D, both for sine and cosine. Those will do the following. C does a horizontal shift. That's also known as a phase shift for these periodic functions. And D does a vertical shift. Now, shifting has some other names out there. You could call it translating. Some algebra books call it translation. You could also call or think of it as sliding the graph. So horizontal sliding would be left and right, vertical shift or sliding would be up and down. And those two numbers, C and D, will do just that, as we will see in our examples. Now that we've seen the various aspects of these transformations according to those formulas involving capital A, B, C, and D, we're going to discuss what is probably the next most important aspect, which is the steps for doing this. And these steps really matter, as we'll see when we finally get to some examples after we denote these steps here. Step 1, which doesn't occur every time, is to use the negative identities that we've already seen previously, and possibly rewrite the equation in a way that has less negative signs, okay? So yes, negative identities can do that for us in some cases, as we'll see. Secondly, we're going to label two periods, or you could also call them cycles, okay? Periods or cycles on the x-axis. And there's actually a little formula that's going to help us with this. So if P is the period of our graph, remember that can be different from the pure periods that we know already, namely 2 pi for like sine and cosine, or pi for cotangent and tangent. The period we're going to identify is possibly adjusted from those, and here's what it is. P, the new period, is going to be the pure period divided by the absolute value of B. Okay, the pure period, of course, that's either 2 pi for sine and cosine, as we're working on for now, or eventually we'll see the other trig functions. Remember, cotangent and tangent both have a period of pi. So when I say pure period, that's what I mean. Those two designated periods for the various functions. If we divide those by the absolute value of B as given in the problem, we will get the new period for the given function that we'll need to graph. Once we graph or label the x-axis according to two periods and the various lengths that might involve, the next step will be to plot the x-intercepts. Now, sine and cosine and many others actually have x-intercepts, tangent and cotangent, but some of the trig functions, for instance, secant and cosecant, actually do not have x-intercepts. So those functions will involve a slightly different step here in step 3, but for most of them, we'll be doing this. We'll plot the x-intercepts. Step 4 will involve us plotting, so let's plot the max and min values using the amplitude or a value. Remember, the absolute value of a is the amplitude, so I'll put that in parentheses here. But we very well will use whatever a is, because if it's negative, of course the absolute value of it would be positive. But the fact that it's negative will matter, and that would do a vertical flip or reflection. So we'll see that happen in the graphs also. Fifthly, we will then shift all these points we've plotted, which have included now the x-intercepts and the max and min values of our graphs. We're going to shift them according to C and D, the horizontal and vertical translations or shifts that will occur. And based on those values that we get from the equation, we'll just simply slide the points left and right some number of places, if relevant, and up and down that number of places. Once we actually shift the graphs, first of all, what we have drawn by now might look fairly ugly if we're not careful. We have to be neat on this. And then lastly, all we do is connect the dots to graph the function. And we should hopefully have a general idea of how these waves look, and so we'll be able to connect the dots with a smooth curve following those patterns. Let's now take a look at an example of one of these graphs. And as you'll see here at the bottom of the screen, I have written y equals -6 sine of -1/2 x. And so we're going to practice using all of our transformations and the steps we already wrote down in our notes here to graph this function. Before we get rolling, let's actually just identify what the variables are that do our transformations. For instance, a, if you recall the general form of the transformation, a is what's in front. In this case, that's a -6. And b, if you take a look back at that transformation formula, b is what you'll find in front of the x term and factored out if necessary. b, in this case, is -1/2. And we'll see an example of that factoring thing I just mentioned shortly. All right, so that's all we have, which is all we need then to put this graph down. Let's follow our steps. You might recall the first step is to use a negative identity if necessary. Now, this is a case when it is necessary. As you might recall, the negative identity for sine states that the sign of a negative input, okay, there's the negative sign. This is the sign of -1/2 x. So that negative fits into our negative identity for sine. We know that this is equivalent then to the opposite or negative of our equation. So -6 sine of +1/2 x. All right, so what just happened is that this negative sign, thanks to our negative identity, popped out in front of the equation right there. So recall, I'll just write it here for a moment. The sine of -x is equal to negative sine of x. That's the general identity that we've established previously, and so I'm just using it right now. This negative sign right in here matches our negative sign right here, and so I'm throwing that, as this one does, out in front of sine as its equivalent, and that's what happens with this negative sign out here. So let's just do a quick simplification on this double negative out front. Of course, those cancel out, giving us +6 sine of 1/2 x. All right, so what we just did was take our original function given, apply a negative identity, and rewrite it in a much simpler form here. So now notice the negative that was out front that might have been concerning us regarding, if a is negative, that would be a vertical reflection, okay? We don't even have to bother with that anymore because we used the negative identity to get rid of the negative that was inside next to the b here and throw it outside, which canceled with the negative there. So now we just have +6 sine of 1/2 x. Okay, that's looking much better. Let's move on to our next step, which is to graph two periods of this, or at least label the axes in that way. So of course, our x-axis here is horizontal, our y-axis is vertical. We have to determine what the new period is for this function. Okay, remember this over here is the simplified version we're going to be graphing now. We want to know what the period of that function is, and we're going to use our b value to do that. So as you might recall, there's a little formula for it. The period is equal to the pure period, or the general period for sine, which is 2 pi, divided by the absolute value of b. Okay, so that'd be the absolute value of negative 1/2. Of course, that's positive 1/2. So 2 pi divided by 1/2, do a little algebra here to simplify this, would end up being 4 pi. All right, so 4 pi is now the new period of our graph. And we got that from our b value of 1/2 being plugged into this formula over here. Okay, well, if we want to graph two full periods, just like we did initially when we were graphing sine and cosine, we're going to figure out how far that is. If one period is 4 pi, two periods would be, well, 8 pi. That's right. And now we'll find that if we just keep cutting this length in half, we get everything we need out of this x-axis. So halfway between 0 and 8 pi would be, of course, 4 pi. Halfway between 0 and 4 pi would be 2 pi. Halfway between 4 and 8 pi would be 6 pi. And then we can cut each of those in half to get halfway between 0 and 2 pi is pi. So now we're just counting by pi. 0 pi, 2 pi. Next would be 3 pi, 4 pi, 5 pi, 6 pi, and 7 pi, and then 8 pi, where we stop at the full length of two periods. Our next step is to plot our x-intercepts. But again, let's leverage what we already know about sine. We're graphing sine here. And the parent function of sine, which just get a little memory of this thing here, right? If this is our x and y axis, the parent function of sine looks like this. It intersects at the origin, and then one full period would be going up, down, and then back to the axis, just like you see up in this cloud here. That's one full period. So notice one full period actually has three x-intercepts, the beginning, the middle, and the end. So let's translate this now to our x-axis. If this is two full periods, then one full period would be from 0 to 4 pi. All right, so let's kind of make that part of our graph look like this little cloud up here. I know it intersects at the origin. I know it intersects at the end of the one full period at 4 pi, and I know it intersects the x-axis in the middle of it. Those x-intercepts, we can just continue in this same pattern. They're skipping every other pi, so 0, 2 pi, 4 pi, next would be 6 pi, and then 8 pi. All right, so those are all of our x-intercepts plotted, which will give us a lot to work with. Next, we want to plot where does this graph go vertically, right? That's all pertaining to our a value, or our amplitude. Now remember, we want the absolute value of a, which of course, given this value, would be positive 6. That means that our graph is going to go up as high as 6 and down as low as negative 6. It's getting a little crowded down here in my graph, sorry. But we know the general pattern of the sine function. We know it looks something like this dream cloud up here. So all we have to do is turn that pattern into something that fits with these bounds. I know it starts at the origin. I know it has to go up to its peak halfway between the x-intercepts, which of course would be right here at pi, and then down to the lowest valley halfway between the next two intercepts, which would be here at 3 pi. So I can plot those points and simply connect them with a smooth curve that looks like our sine curve. All right, and all I have to do is continue this pattern for the second period to make this all finish. So at 5 pi, it's going to hit up at its max again, and at 7 pi, again, down at its min. Okay, those maxes, again, remember they're 6, and the mins are negative 6, and we got those values from the amplitude being 6, which we got from the a value. Let's take a look at another example. This time we'll graph y equals negative 2 cosine of pi over 4x. All right, so we're going to get through all the transformations and identify them. Let's start by just realizing what the variables are. For instance, capital A, our leading coefficient here in front, is negative 2. Okay, that means a couple things. First of all, the fact that it's negative means that this is a vertical, or will be a vertical reflection. Okay, we'll see what that turns out to be. The amplitude, which is the absolute value of A, will be positive 2. Okay, so that means we have a vertical stretch. Our B value, in this case, in front of the x here is pi over 4. That's going to affect our horizontal stretch or shrink, and we'll figure out what the period is based on that. This time, notice there's no negative identity to account for. We usually try to do that first if needed, but the negative identity would show up as necessary if you see something negative as a b value. There's no negative sign in front of it, so we don't need that. Let's go ahead and determine our period with our little formula. Period is the pure period for cosine, that's 2 pi, divided by the absolute value of b being pi over 4. All right, so if we reduce that, we'll end up with 2 pi times 4 over pi. If I flip the denominator, do the reciprocal thing, cancel the pi's, and end up with a period value of 8. All right, so that's going to help us label our axis, which is our next important step. We have x-axis, y-axis vertically here. And then once we get the period labeled on the axes, we'll be able to mark all of our important intercepts, maxes, mins, all that stuff. If we want 2 periods and one of them is 8, of course, I'll be extending all the way to 16. All right, that's 2 periods. Of course, one of them, half that much, would be to 8. And now let me mark all the half places in the 2 periods we have listed here. Halfway between 0 and 8 would be 4. Halfway between 8 and 16 would be 12. And then we'll mark halfway between all those places. These are just integer values, which is nice. So halfway between 0 and 4 is 2. 4, 6, 8, 10, 12, 14, 16. So all tick marks currently are just multiples of 2. And we might have to add some marks to this, of course, but for now, that's a good setup. Now, let's recall that one period would go from 0 to 8, and the next one would go from 8 to 16. But it's always good to remember what the parent function looks like. So this is our cosine function. Let's do a little cloud sketch up here to remember what this is. Cosine the parent function, the basic one, starts up at the max, goes down to its min, and then all the way back up to its max to do one full period. That means at the beginning of our period, we're actually going to use the max value, hit its min halfway between the first period, and then get back up all the way to its max. Now, there's one issue with this one we have to consider, which is our a value was negative, which remember, we said that's going to mean a vertical reflection. All that means is that we flip the graph upside down. So what normally starts as a max on the y-axis is going to start actually as a min if it's vertically flipped. And we know since our amplitude is 2, that our maxes will be up at positive 2 and our mins will be down at negative 2. Again, given that the a value is negative, that means a vertical reflection. Our y-intercept is down here at negative 2. This graph's going to shoot upward, hit its max halfway between the beginning and the end of the first period, and then back down to where it started at the end of the period, which is at negative 2. All right, so halfway between 0 and 8 is at when x is 4. We know we're going to hit our max value there. So I'll plot that. And then halfway between all these mins and maxes will be the x-intercepts. So we have one at 2 and one at 6. All right, well, the a value has been dealt with because we know the amplitude is 2 and we know it did a vertical reflection, which means we started way down here at negative 2, went up, and then back down again for one full period. The b value adjusted the period. The new period was 8, and we used that to label our axis values. And then we cut those in half to get various important places. There are no other transformations in this original equation. There's no c value, there's no d value. So we're done. All we have to do is finish the points being plotted and then trace them to get our full graph. If you continue the pattern, you'll notice we go start at the min, max up at 4, min at 8 again. The next max would be up at 12, and then the next min would be down at 16, and the x-intercepts would be halfway between those. And hopefully you're seeing all the patterns as you start just counting by things. All the x-intercepts occur at 2, 6, 10, 14. You're just adding 4 to each of those x values to get the intercepts. Now that we have all these important points plotted, we'll go ahead and connect them with a nice smooth cosine curve. Remember, we're going for accuracy, not artistry, but do your best to make it a smooth looking wave or curve that connects all of our important points. So there we have it. That is the graph of y equals -2 cosine of pi over 4x. For this last example, we're going to take a look at everything all put together. So notice at the bottom of our screen, we have an example which is y equals 3 times cosine of, so open parentheses, -2x plus pi over 4, close parentheses, plus 1. All right, well, let's take a nice look at this one using all of our different transformation values. So a, the coefficient in front of this is 3. Notice it's positive, so we don't have a reflection here vertically. But this does tell us that our amplitude, the absolute value of a, is 3. Now, b needs a little bit of work before we identify what it is. Notice in this case, we have 2 terms inside the parentheses, with our x being there as our variable. The coefficient of x is -2. If that coefficient of x is not 1, meaning you actually see something there, you have to factor it out of these 2 terms inside the parentheses. So we're going to rewrite this entire equation as 3 cosine of, okay, now inside the parentheses I'm going to factor out the number in front of the x I see, which is -2. I'm going to factor it from those 2 terms, which means left I have x, positive x, and then minus pi over 8. Of course, we'll end with our plus 1, our d value there eventually. Now, finally, we can see clearly what the b value is as -2. If you compare this to the general transformation formula we wrote down a lot earlier, you'll notice that's exactly where b shows up, and so b in this example is -2. Now, of course, the b value will help us identify our period for this new transformed function. We know the formula for the period is going to be the pure period of cosine, which is 2 pi, divided by the absolute value of b, which would be +2. Okay, reduce that, and we get pi. All right, so 1 period for this transformed function is pi. If I want to go 2 periods graphing out, that means, of course, I'll go all the way to 2 pi. I'm going to label this as my x-axis. Horizontally, vertically, I have my y-axis. All right, we have the full 2-period mark of 2 pi plotted. Now let's put all of our important x-axis markings on. I'll cut this in half, which would give me pi. I'll cut each of those pieces in half. So from 0 to pi, I have pi over 2. And from pi to 2 pi, I have 1½ pi, which is 3 pi over 2. And then I'll cut each of those in half one more time to get pi over 4, 2 pi over 4, 3 pi over 4. You can just kind of count by pi over 4s or find a pattern quickly to mark all of these places. Well, that's like 1 pi over 4, 3 pi over 4. This would be 5 pi over 4, halfway between pi and 3 pi over 2. And then, of course, 7 pi over 4, halfway between 3 pi over 2 and 2 pi. All right, so our important places on the x-axis are plotted. We know that our amplitude is 3. There's no reflection, vertical reflection in this. So let's recall what the parent function of cosine looks like to make sure we have the correct pattern going here. Cosine starts at the max, dips down, and gets back up to the max for 1 full period. That max value is located at 3 thanks to our amplitude, so I'm just going to mark that max place as 3. Of course, then it's going to go all the way down to -3, so I'll mark that also. Cosine starts at its max, so 0, 3 is a point, and then it ends at its max with 1 full period. So at pi, the end of our first period, I'm going to hit the max again. Halfway between those, I hit the min. So down here at when x is pi over 2, I get an output of -3. And then halfway between the maxes and mins, of course, is all the x-intercepts. So at pi over 4, we have one, 3 pi over 4. We're just going to keep this pattern continuing, so we hit our next min at 3 pi over 2, and then lastly our last max at 2 pi. Halfway between those we have our intercepts. All right, so we have all the maxes, mins, and x-intercepts plotted. That's a major step. We got it. If you look at the general formula for the transformations, the formula itself has x minus c in it. So we actually have to use the opposite of the sign of this fraction here we see for c, which means our c value is positive pi over 8. And lastly, our d value on the very end there is a positive 1. So remember, c and d shift things left and right, up and down. C will shift everything to the right, pi over 8, and d will shift everything up 1 unit. Now, pi over 8 is less than we have graphed on our x-axis, but not by much. If you take a look at the first tick mark, it's from 0 to pi over 4, so half of that would be pi over 8, which means if I just cut everything I have on the x-axis already in half, those will give me all the pi over 8 distances I might need. I'm going to extend, of course, past the normal end of 2 pi because we're going to be shifting to the right. So let me mark this off. C being pi over 8 means we're going to go right that much. D being 1 means we're going to go up that much. So in fact, I have 3 already marked as the max. I'm going to have to go up to 4. And I have -3 marked as the min. I'm going to have to go up to -2 so I can shift everything up. All right, now that we have all of the markings on the x-axis, all of our parent function points, or at least some of them plotted, I'm going to do the shifting as our last step for C and D. Given the way we've marked the x-axis, the convenient thing about that is all we have to do is shift every point right 1 tick mark, and then, of course, up 1 tick mark. So I'm going to go for every point right, up, and that's where all the new points will end up. So we'll do that with every one of these. Right 1 tick mark, up 1 tick mark, there's a new point. Right 1 tick mark, up 1 tick mark. This happens for all of them, even down here. Let's see, right 1 mark, up 1 mark, right 1, up 1 tick mark that is. The horizontal right 1 is not 1 unit, it's 1 tick mark, which represents pi over 8, as we said earlier. All these points are going right 1 tick mark, up 1, right 1, up 1. And we'll end here, pi over 8 past 2 pi, which is the last place we have there. Finally, it looks like a mess, but hopefully we can tell which are all the endpoints or the finished ones. Those are the ones we want to connect. So I'm going to see what I can do to draw a nice, smooth cosine curve that connects all of those points. Go slow. Look ahead before you start drawing. It's easy to forget which point you're trying to connect here. Remember, accuracy, not artistry. So all the correct points are hopefully plotted at this point. And that, folks, is how we can transform using every single transformation. There's an amplitude that's different, which is a vertical stretch because A is +3. There's a horizontal shrink in this case. You can tell now the period of cosine is normally 2 pi. In this case, it was shrunk down to be just pi. C means we shifted right, pi over 8, and D means we went up 1 unit. 4 different transformations happening in one graph.